Okay, so we can start. Any questions about this, which we did exactly a week ago? We started exponential generating functions, which is instead of the series, in this case, for example, in, instead of this in series being stored, you stored in by n factorial. Okay, and define the suitable generating function, which we call, we now call it an EGF for the series I of n. Okay, and we had this nice example of involutions, counting the involutions, which comes out to be somehow related to the factorial. This example was clear? Okay. Will we have what? Here. Plus 1. Why do you have plus 1? So initially this was 0, right? So oh, because we have divided by n minus 1, and that is 0. N minus 1 is 0. Okay. I have to check. But what do others think? Do we have to change this, or is this fine? Yeah, again, I mean, I think this is the same argument last week also I was making, that once we have substituted the recurrence, even at n equal to 1, you are no, but now the problem is that coming from first step to the second step, we are actually dividing by 0. So that may be an issue. We replaced n minus 1 factorial by n minus 2 factorial. That's a division by 0, right? So looks like we have to correct that. Yeah, but let me not resolve it here. So this may need a correction of a constant, but still you can solve the differential equation and get a similar result, if not identical. Okay, so there is another example which is actually more complicated, and we have mentioned this in the overview of the course, which is to count the number of partitions, unordered partitions of a set. Okay, that is also where EGF is useful, and it gives a pretty complicated generating function. So another example. Which is number of partitions of a set, which we can just fix to be 1 to n. So the thing is that this is not, we are not partitioning a number, we are partitioning a set, right? So this is exactly the same as throwing balls into bins, except that balls are distinct and bins are identical. So this is also equal to number of ways to put n distinct balls into n identical bins. Which we did not expand upon during the overview because this is not so easy. But now using the recurrence method and then the EGF method, you can get a good grasp on this expression or on this count. So let's call this Bn. What is the recurrence for Bn? What is it? Can you guess? You must have seen this somewhere. So recurrence for this happens to be n minus 1 choose I minus 1 times b n minus I, and I goes over all possibilities 1 to n. Now given this expression, can you reverse engineer the proof? How do you show this? So somehow Bn you want to reduce to B of n minus I for all possible I, right? How do you do that? So actually the starting point will be the same as in that Pingla's problem, where we said that okay, the last possibility are 2 and then we divide it accordingly. So here we will we can say that focus on the element n and divide into cases according to the elements which are in the same part of the partition as n. Okay, so what are the neighbors of n, say? So the possibilities are, the first is that how many neighbors are there? So what is the size of the part? It can be just n, or it can be one more element, so 2 elements, 3 elements, n elements. Right? Those are the n size possibilities. Within the size possibility also you have possibilities, right? Because if you say that the part with n has 2 elements, then there are many ways to select that second element. Right? So you can divide first in terms of size of the part containing n, which is what I represents, and then after fixing I you can calculate the number based on b of n minus I, because the part with n has size I. So the remaining, so once you have fixed this part, the remaining elements are only n minus I, and on those remaining elements it's again the same problem. No, the part with n size is at least 1. So n is the element present and some other unknown stuff or unfixed subset of this set 1 to n. And then this is a problem of size, again n minus I sized problem, sub problem. Okay, this would be the division, and this size is I. So let's write this formally. Consider the, let me say, in a partition consider the part, because there will only be one part, right? N cannot go into 2 bins, say, n will go to only 1 bin, and the bins we don't order. So so we'll just call it a part, so the part which contains n. Okay, so in the picture, that's the, which is probably not visible, but it's not very important. So the box which contains n, we are saying its size is I. Sorry, define it to be I. And I goes from 1 to n, right? All these possibilities are there. I cannot be 0 because, well, you have already put n in there. So I can only go from 1 to n. And that is basically what the summation is over. It's over these i's. Is that clear? That's the starting point. And after that, it's an easy road, because now you can just count how many possibilities are there for this part or for this bin that has n. So number of such parts or bins is equal to, so I minus 1 elements are missing, are unfixed, right? Out of how many elements? N minus 1. So that is the definition of choose. So n minus 1 choose I minus 1 is the number of ways you can fill these dots. And then the bin is now this bin or this part is fixed completely. Now you can focus on the rest of the bins, right? Which is these black dots. So that is the n minus I part. It's actually now the same problem as we started with, right? It's same problem on a smaller size, because I, remember, is at least 1. So this problem is now of size n minus 1 or smaller. So it's a strictly smaller problem, which I am calling sub problem. And there again you have these, if you think in terms of bins, there are n minus 1 bins or less. They are unordered, and you want to partition the remaining set, which is of size n minus I. So let me write in terms of count. So number of ways or number of partitions on n minus I elements is then by definition B on n minus I. Now on this, the black count and the red count, you will do what? Can you do the product rule? You can do the product rule, because for every choice on this in this black count, there is a independent choice in the red count, right? So you can multiply it. You apply the product rule, and after that, as you change I, what happens? You apply the sum rule, because I is different. So different sized parts, in particular different partition. So you count them separately. There is no overlap. So by sum product rule, you will get that if you sum up over all i's, then you cover all possible partitions of n. So that's Bn. Is that clear? So this is a famous recurrence. Now, how do you solve this, or how do you get some understanding of what this function is? B as a function of n, as n grows. Does this recurrence give you any idea? Is it a known number? Okay. So clearly the silence suggests that it's an unknown number, and it's not easy to calculate. So we'll not calculate it, we'll leave some major part as an exercise. Obviously, since it comes under EGF, you have to use EGF. So you define theta t now to be bn times t to the n by, oh sorry, not n, bk times t to the k by k factorial, all the k's, non-negative. Right? Define this infinite power series, formal power series. So that's an EGF of pk of bn. And yeah, then like we did before, that's the common trick for EGFs. We use the derivative. Okay, so you differentiate this just defined EGF. Theta is a function of t differentiated with respect to t, and you write it as study this via the recurrence. To get this d theta by dt, what do you think you will get? Yeah, this may not be very easy to see, but this n choose I is like n factorial divided by n minus I factorial multiplied by I factorial, right? It's roughly of that type. So you have to do some calculations which I am leaving as an exercise, and you will get this theta times e to the t. Okay, this will be the recurrence. So this is a differential equation. It looks very different from what we got for I of n for the involutions, but it's very easy to solve. What do you think is the solution? E to the power? E to the t. Yeah, almost that. So show that you get theta t to be e to the power e to the t minus 1. Okay, so these are just simple calculations you can do. The ideas are all here. And you will get something like e raised to t. So now you can go back, once you have the function in some good form like this double exponential, then you can go back in the power series and you can recover the coefficient of t raised to n, and whatever you get, that is the idea of Bn. That gives an estimate for Bn, right? So you can potentially compute this on a computer now, faster than just applying the recurrence directly. Yeah, so this is called, Bn has a name, it is called Bell number. Okay, so the coefficients of this power series, they are called Bell's numbers, and they are the count many things, but in particular here they count number of partitions of a set. So what we'll do next is slightly different topic. So now we'll go to combinatorics in general, and we'll see some combinatorial techniques and give many interesting examples. Okay, so through examples you will learn these techniques, and you will see them more, of course, in the assignments and tests. So today let's start with inclusion exclusion and see how much time we have. Yeah, so we'll actually do some very simple combinatorial tricks. Combinatorics is currently, I mean, by now it's a very advanced subject. It's very vast. What we will do is just some very simple things that you all already learnt in your school or JEE. But I'll try to challenge you with harder questions than just JEE, especially in the exams. Okay, so first technique will be inclusion exclusion. So the principle of inclusion exclusion you have seen many times. Let's just repeat it. So suppose we take this silly example where there are 100 students, and you basically want to, you have some data about which social media sites they visit. Or so they use, let's say, WhatsApp and Facebook and Twitter. Yeah, I'm skipping Instagram, which is probably more popular amongst you. So the number of students who use WhatsApp is, let me say it properly. So 44 use Facebook, 50 use Twitter, 56 use WhatsApp. Now, of course, this, if you add this up, it is more than 100, right? So it means what? It means that there is an overlap, right? So just this much of information is not at all enough, because you don't know how many are using all these sites, how many are using none, how many are using two, even in two, which two, right? So that information is what the principle of inclusion exclusion deals with. So it basically deals with set intersections. Okay, and as the number of, so here the number of sets will be 3, and the principle we'll get from this example, we'll try to generalize it to arbitrary number of sets, when you cannot do it by hand as we'll do here. So we have to do it more abstractly. But let's first find some trick in this example. So next you will need the information of intersections 2 at a time. So let's say 27 use Facebook and Twitter. Okay, this is for the intersection. So both Facebook and Twitter, 27 use, 31 use Facebook and WhatsApp, and 34 use WhatsApp and Twitter. Is this information enough to deduce the sizes of the 3 sets and all the intersections possible? Why not? Yeah, because without going into the exact numbers, just abstractly you can say that still this is not enough to tell you how many use all 3, right? And the dual of that is how many use none, right? Those 2 things are missing. So based on what one is, the other will get fixed, right? So there are 2 unknowns. Actually, there are these 2 things unknown, but they are related. So there is one unknown, and that one unknown can be anything. So that unknown also has to be fixed. So we decide to fix the intersection. So 19 use all 3. Okay, so now the information should be complete, and you can see this in a picture called the Venn diagram, where you can write down not just the 3 set of students who use Facebook, respectively Twitter, respectively WhatsApp, but also intersections 2 at a time, intersection 3 of all 3. So let's do that. So you have, so this is Twitter, this is WhatsApp, and this is the set of users for Facebook, right? That's the usual Venn diagram. Now, where should you start filling in data? From the inside, right? So this 19 will go here, because this is the place where students are who use all 3. And after this, can you find out what is the intersection of Twitter and WhatsApp minus 19? So this represents those students who use only Twitter and WhatsApp but not Facebook, right? Exactly 2 of these sites are used. So that will be Twitter and WhatsApp was 34, right? So you get 15 here. And symmetrically, or similarly, you will get 8 here and 12 here. Okay. And from this, can you now calculate students who use only Twitter? Right? So that will be 8, 10, and 5. Right? So you get 8 by adding up 34 plus 8, that is 42, and Twitter was 50, so you are left with 8, right? And this symmetric thing in other spaces. So after this, how many students are there who use none? Right, so that's the outside, right? So this is the complete Venn diagram. And these numbers add up to 100. So we fill this Venn diagram by moving inside to outside. So we started with the inside, which is the common of all 3. Went to the outside, which is 23, right? And there is no other way to do it, because without putting 19 there, you don't know anything else. You only know the kind of the aggregates here and there, but you don't know exact values in the smaller spaces. Okay, so so what we'll do now is we will we'll count it in a different way, which is doing it outside to inside, and that will be a bit more complicated. That will give our formula for inclusion exclusion. So let us try to do this outside to inside. Although this is not properly defined, so you will see as we develop this. So this will help when the number of sets is large. Okay, so we want to now develop a formula which is more systematic, more abstract, so that even when the sets are like hundreds and thousands and maybe variable n, so when it is impossible to draw these pictures, still we can do a calculation to, let's say, count the number of students who are outside the union. That is what we are interested in. So, okay, let us now, with the previous experience, let us now define these things formally. Okay, and it will look complicated, but you can go back to the picture and just specialize to that whenever there is a doubt. So let U be the universe of students. And let A1 to AN be subsets. Okay, so basically in the previous example, N was 3 and A1, A2, A3 were these 3 sites. The students who visit, they form the subset A1 respectively A2, so on. And what we will need, like we needed before, is for every subset I of 1 to n. So how many subsets are there of 1 to n? 2 raised to n, right? So as n grows, the number of these i's will be large. Okay, so the picture will be impossible to draw, because here you just had 8 numbers. In general, it will be 2 raised to n, so it will be impossible to draw. So we have to do this symbolically. So for every subset I of 1 to n, you consider or you are given A sub I, which is the intersection of AI. Okay, this is the definition of AI, A sub I. So just think of this as Twitter intersection WhatsApp, then WhatsApp intersection Facebook, and then finally the intersection of all 3. Right? So that information is given to you. In fact, actually we will not need the information for the set, but just the size of it. Okay, so I'm writing it here as subsets, but the formula will just use the size of A sub I. So bar A sub I bar. Just that information will be needed in the formula. So what we are interested in is the union of AIs and things outside it, so complement, or in other words, U minus U of AI. Right, so we are interested in this subset union of AI's complement, and we want to compute its size as a function of whatever is given. Is the question clear? So what is the formula? So union AI complement is equal to, the size of this. The size of this is equal to use these A sub I information, size of it, over all the subsets. And what is missing? Yeah, there are signs. So some A sub i's will come with positive sign, the others will come with minus sign, and together they will give you the count. So what is the sign? It depends on, parity of the size of I. Okay, so when I is 0, this is plus, or when the size of I is even, this is +1. When it is odd, it is -1. So in particular, when we are looking at singletons, right, just Facebook, just Twitter, just WhatsApp, then that comes with a minus sign. Is that right? Then I should also define A empty, I guess. What is A empty? So A empty is everything. Yeah, that's the definition. So when the size of I is 0, it comes with a positive sign and it actually counts the whole universe. Okay, that's the, you can say, the first order approximation. The complement cannot be bigger than this. It can only be smaller. So you get the size of the universe. When you go to the next order approximation, then you will be looking at A1 or A2 or A3, their sizes, and you will subtract from the universe. Okay, so that will be the second order approximation. And when you go to I of size 2, then you will be looking at intersections of these, their sizes. And that you will add or subtract in the formula. So when I is of size 2, it's a +1 sign, right? So you will be adding it. So you alternatively from the universe subtract, add, subtract, and so on. And if you do this till the end, then you will get the size of the complement. Is the claim clear? Do you know how this is proved? How? Okay. So yeah, so I'll give a different proof. But this is what we call principle of inclusion exclusion. Okay, because this sign business, it is including and excluding. In this order, from the universe, it first excludes, then it includes, and so on. Okay, so let's try to prove this. So the idea is we consider the count of, you pick an element from the universe and see whether it is being counted correctly. So fix an element small u from the universe and check how is it being counted. In the right hand side. So what it means is if the element small u you have fixed, it is in the complement, right, then it should be counted how many times in the RHS? You have to check that it's counted exactly once and not twice, not thrice, not zero. And if the element u that you have fixed, it is not in the complement, which means that it is in one of the AIs, then the count in the RHS should sum up to zero. Right? This is what you want to do. So you want to show that for small u, the RHS is either 0 or 1 in the correct direction, and no other value is possible. Is that clear? So that is a very special thing, because the RHS seems to be an arbitrary expression. So it could have been any count. It could also have been a negative count, for all you know. Right? But we will show that actually everything balances out. And ultimately small u, that the element you have fixed, will be counted exactly 0 or 1, depending on whether it is not in the complement or in the complement. So yeah, case 1 is simple, which is if suppose u is in union AI complement. Right? If this is the case, then can small u be in any of the AIs? It cannot be, right? So this means that this small u is not in AI for all I. If it is not present in any of the AIs, then it cannot be present in any of the A sub big I's. So in the RHS, actually none of the cardinality is counting the small u. Right? So everything is 0. So this is the easy case. So which means that RHS count is 0. Okay, so sorry. Yeah, that's a good point. So why is that not the case? Something is wrong. Sorry? No, so small u is not in any of the AIs. Why is the left side 1? Oh, sorry, yeah. Okay. So, but yeah, I should add here. And obviously small u is in U, which is A empty by definition. So U is not counted in any AI except and yeah, the left hand side it's counted once. So this case is done. Let's do case 2. So case 2 is much more interesting. U is not in the union complement, which means that it is in at least one A sub small I, and possibly it is in many. Right? It could also be in all of them. So this is the hard case, because then many of these in RHS, many of the the size of A sub i's, many of these are counting U. Right? Sometimes the count is with -1, sometimes it is with +1, and you don't know what will be the sum. It can be negative, it can be positive, it can be 0. Right? On the left hand side, on the other hand, the count is 0. Right? So you have to show that 0 is equal to 0 in this case. The previous was 1 equal to 1. In this case, you want to show 0 equal to 0. So U is in AI for some I, and possibly for many i's, but at least for some I it has to be there. So here we have to actually give a count, and we have to do this exactly, right? We don't want an estimate, we want to exactly show that it's 0. So let us do that. So for that, let's define first consider these places where U lives, right? So that I'm calling J sub U. So these are those i's, or maybe j's, those j's 1 to n such that U lives in AJ. And this is non-empty. Right? Because we have assumed that, we have deduced in this case that JU will at least be a singleton, and maybe its size is anything between 1 to n. It's not 0, that's all we know. So let's define the size of JU to be K, which is positive. Okay, and now we can calculate A sub i's, the A sub big i's properly, because the ones where big I is a subset of JU, what happens? If you take those AJs where J is coming from J of J sub U, what can you say about the intersection? U is present in all these AJs, right? So the intersection also has U. So A sub i's where big I is a subset of JU, there the count is 1. In all other i's, the count is 0. Right? So you now can expand the right hand side. So let's keep this observation that A sub I has U if and only if this I is a subset of JU, right? Because remember what AI is. AI is the intersection of these sets. So U has to be in all of them, which means that all these subscripts, they have to be in JU, which is what I being in JU means. Any questions? Okay, so with this, we can now expand RHS exactly. So this means that the right hand side in the original formula, principle of inclusion and exclusion, the right hand side is equal to -1 to the size of I with a 1 being counted only in those big I's which are subsets of JU. Is this fine? So this 1 is, so this value, underlined value is 1 for those sets which are subsets of JU, and it is 0 otherwise, right? So the 0 ones we can drop it, the ones we have to count, and this number can be anything, can be negative, 0, positive. So what do you, how do you think you show this to be exactly 0? You don't know JU, you don't know, I mean U is also an arbitrary element in the universe, so you don't have any information. How do you show that this count is 0? No ideas? Number of? Right. But these i's are now subsets of JU. So yeah, so okay, JU was of size k, maybe you should remember that. Remember that JU is k, so we can just think of this as the set 1 to k. The subsets will be 2 raised to k many, right, then? But this is still, there is a sign coming. Sorry? Right, so actually you can write down the exact expression in closed form because of binomial series, binomial expansion. So what happens next is the following, that's the magic, that so for I of size, let me use something else, L. For the subsets of size L of JU, the contribution is so basically we are fixing the size of I, right? So size of I we are fixing it to be L, and now we are counting how many times does -1 to the L appear. That will be k choose L, right? And then you sum up over all the L's. L goes from 0 to k, all possibilities, -1 to the L, k choose L. And what is this? This by the binomial expansion is actually exponentiation by k of 1 minus 1. Right, and this is the reason why you get 0. So you don't need the exact set JU for this. Just by the sizes it actually matches up. Okay, and this this trick will appear in many other proofs. So hence both the cases are complete, and in all cases U is counted correctly. For all the universe elements, the count is correct. Okay, and when that happens, then we can say that we have correctly, the claim that the left hand side, what we wanted, has been exactly computed. Is it clear? Yeah, so there are other proofs of this principle of inclusion-exclusion that you can try, but this seems to be the simplest. Okay, so let's quickly finish up with an example of example where you can apply this formula, And that example also you must have seen, I'm sure. So the example of derangements. We gave it in the overview. So derangements are those permutations where every element is moved. No element gets fixed. Right, and traditional way of posing it is you want to put n letters into n addressed envelopes. And let me add that these are distinct. Okay, so there are n distinct letters which you want to send to respective addresses, and envelopes are addressed already, and then you want to put one letter each in one envelope, and a derangement will be when every letter is misposted. Every letter goes into a wrong envelope. So basically you have to count how many such arrangements are possible. Okay, so what is the size of derangements? So how do you apply the formula? What is the set A sub I? So frame this as union AI complement. Right, so how do you frame this question? The AIs will be AI is that the ith letter was correctly posted, right? So basically arrangements with letter I correct. Okay, so this is the focus is on the ith letter. Now the union of AI means that something was correctly posted, and complement is nothing was correctly posted, right? And hence you really want to count the union AI complement size. So now you apply the formula. So this principle of inclusion exclusion, this implies that the number of derangements what was the formula? Times the size of A sub I, right? How do you calculate this? So for example, how do you calculate A1 intersection A2? Or how do you calculate before that size of A1? How many arrangements are there where one was correctly posted? Yes, so you post one, put it in the first envelope, and then the remaining is arbitrary, n-1 factorial, right? Similar thing for first and the second letters. First and second, there is only one correct way. You fix that, and after that n-2 factorial. So you get easily that the size of AI is n minus size of I factorial, which means that number of derangements is equal to yeah, let me do it in 2 steps. So first step is just copying this. And finally, you can simplify it because this value n minus I factorial only depends on the size of I. So you go over all the sizes. So that will be L equal to 0 to n minus 1 to the L. Okay. So L goes from 0 to n minus 1 to the L times n minus L factorial. And how many times do you see this contribution? The number of subsets there are of size L, which is n choose L. Right? So we can finish there, but if you wanted to simplify, it can be simplified. You can bring out n factorial, and you can then see, so n minus L factorial gets cancelled, so you get this by L factorial. Okay, this is the answer. Is this clear? Can you approximate this? How far is this from n factorial? Sorry, 1 by E. Yeah, so you can show that this is actually quite close to n factorial by E, right? And E is like 2.78 dot dot. So this is very close to n factorial by 3. Okay, which could be a bit surprising. Amongst all possible ways to put envelopes, 1/3 are derangements, right? So 1/3, there is a 1/3 probability, in fact more probability, that every letter will be misposted, right? This you cannot guess in advance unless you do this calculation. Any questions?